This, of course, just tells us that E squared plus m squared, right? The Einstein dispersion relation, okay? And the particle is a shell. And this, of course, means that k mu epsilon mu is 0. Important because there cannot be 4 degrees of freedom. This is a spin 1 particle, okay? What else we've done? We've written a propagator. You've done it. And we know that the massive propagator is minus I g mu nu. And it's k mu, k nu. It works perfect at low energies. We are unhappy with the high energy behavior when k goes to infinity. Okay, we said we don't have to worry about that. By the way, maybe just to make sure, any questions on the homework? Anything clear, not clear? You will have to do just to make sure you look at the polarized W decay to understand what is happening physically. So you start, the bulk of the problem is doing W polarized in the, say, upper direction, okay? Upper Z direction. So we start with, and then you will show that the amplitude, or if you wish, the partial decay rate, I don't know if you had a look, d gamma over d omega will be proportional to 1 minus cosine theta squared, where theta is the angle of the electron motion. Okay, the way I did it, okay, I gave you my notes just in order to be pedagogical using the usual trace formulas. They are useful, okay? Trace formulas are very convenient because you can apply it to any problem. But sometimes it's good to see explicitly what is going on and to work with the spinner that corresponds to the state instead of just summing them. You can try both if you wish. Because I've asked you to take the fermion mass 0 in the decay, which is in this case electron mass. Neutrino really is practically massless. And then you can use the argument of helicity or chirality. You have only left-handed guy which has a fixed helicity. You can construct the state, right? If the electron is moving this direction, say, in the Z direction, how would the two-component state look like? We could call it EL, electron. There is a normalization of square root of 2E. So it happens. But I'm asking you the form of the, it will be two-component really. If you wish, it will look like, maybe, let's write like this. EL, or psi L, would look like U0 with the convention of gamma 5 that we have, okay? The left-handed is the upper guy. And U would look like square root of 2E. Well, I remind you in the notes, but you should remember that the helicity of the left-handed fermions is, or maybe you don't know that. You should know that, or maybe you don't. I'm just thinking. Anyway, it's in my notes. They have a fixed helicity, of course. They're massless particles, right? So you can't stop them. So the only thing we can talk about is the projection of spin on the direction. It's minus a half. This is a conventional left, which it means that you are correctly fixing the signs of gamma 5 and so forth. Helicity simply, by definition, the projection of spin on the direction of motion, which is sigma over 2 times p. So if it has a helicity minus a half and it's moving up, then the spinor will look like, if it's moving up, then P in this case would be Z, you agree? And therefore, helicity would be simply sigma 3 over 2. Operate. Agree? And it should be minus half, therefore it will look like so what are the eigenstates of spin half, right? They are 0, 1, and 1, 0. It would look like this. You could do two things. You could, it's moving in the theta direction. We want to do the general case. Actually, there is an azimuthal angle phi. I'm taking a 0, you should think about I'm taking a 0. Physics should not depend on phi, right? There is that symmetry still when I fix. But anyway, you can do that. You can rotate the spinner, or you can solve the equation, right? In general, P, we have the form cosine theta. If you want to keep phi, cosine phi. Sorry, sine theta. Sine theta, sine phi, cosine theta. And you can solve this equation. You can explicitly construct the spinner. So you can shortcut the calculation. You don't have to do the trace formulas. You could do that if you wish. You don't have to, because it's not in the homework. And it's an advice if you want to understand deeper what is going on. Because there is an interesting result coming out. Can you, well, you have to comment on that. Can you think where it's coming from? We are not going to discuss it here. We'll discuss it in the future. It says that the amplitude vanishes when theta is 0. It says the electron cannot go up. This is the famous parity violation of weak interactions, okay? Instead of being symmetric, it likes to go down, it doesn't like to go up. Can you guess what the reasoning is? Well, it's angular momentum. Give you a hint. Think about the angular momentum, the particle is at rest, think of the total angular momentum.
This neutrino is left-handed, so if the electron goes up, then the neutrino has to go down. And then you cannot conserve.
Not because it's left-handed. If electron goes up, neutrino has to go down. That's conservation of momentum, right? Sorry.
Yes.
So if electron goes up, neutrino goes down. I won't solve it. This guy has helicity minus a half.
So spin.
But you have to think of the total. So okay, you should go on. Okay, then you should think what happens to this guy. Okay,
yeah.
This is an antiparticle. That was in the first problem. The properties of the antiparticle. If any of this is confusing, use the trace formulas, you can miss it. Okay, and you just read it in my notes. I don't want to say too much. I want to see if any of you will like to do this on your own, and then we can discuss it next week. This is sort of easy to guess. When it's longitudinally polarized, it's fun to guess how it will depend on theta. You know, you can know this reasoning. Why it's good to do these things? It's just because when you do the calculation without the physical intuition, then you don't know what's going to happen. It's good to know in advance, or it's good to have a check on your result. Okay. For example, it should be 1 minus cosine theta. It should not be 1 plus cosine theta without conventions. As we can discuss in the future. Okay. Let's leave it at this point. You're okay. No questions on this. Okay. You think you understood. Okay. There was a question, I think it was Julian who asked me, what about the potential? How do I derive from the fast-moving physics of high-energy field theory, the non-relativistic static potential, right? And why do we do that? One last exercise with the massive Rocca field. So imagine that I look at the scattering of electrons. Let's say enters with momentum P1 that becomes P2, K1 that becomes K2, What propagates here is momentum q. How would I compute this amplitude? Okay, the rules are, I start with an interaction which is, no, let's call it E. Let's really take the interaction Lagrangian to be this. Let's take an electron with a charge convention like this. What is the Feynman rule that you've learned? If the coupling is E, what do I put in the vertex? Minus IE, right? It's very important, it's minus I. The Feynman rule in momentum space is minus I times the interaction. Minus IE twice. Then what I have here, psi bar gamma mu psi, I could call J mu, you agree? J mu. Then I have the propagator. I want to have a compact form, d mu J nu. This is what I have. And maybe we just write the propagator immediately and we use the privilege of the blackboard. There is a minus I. I want to be careful now with the factors. G mu nu minus Q mu Q nu. I'm going to add a small mass to the photon, just to have a generic result. So if tomorrow you ask me what about the massive gauge boson, like the Z boson, I have the result there. Okay, so why don't we be more general? I'm sorry. Let's take any interaction with any coupling constant, G, so that I can apply it to proper field. MA squared, Q squared minus MA squared, J nu. Okay. Now, the things that you know, that the current is conserved. So when the current is conserved, I want to apply to the conserved current. Well, I have two arguments here. In the case of QED, the current is conserved, so the conservational current, d mu psi bar gamma mu psi is equal to 0 is equivalent to Q mu J mu equal to 0 in momentum space, right? The time derivative will become Q mu. So this drops out. If the current is not conserved, it will drop out anyway. I'm interested in the low energy limit of the theory, which we will see in the moment. You will see how it drops out. The Q square is Q0 square minus Q square. And this will be, for example, P2. So E2 minus E1 square minus P2 minus P1 square. Non-relativistic limit, energy goes difference faster to 0 than the momentum difference, because the energy is m plus p square over 2m, right, in the non-relativistic case. So E2 minus E1 is of the order of P2 square minus P1 square over 2m. It's square in the moment, and I have to square it. So I can ignore Q0. This is going to be small. So obviously even Q0 will be small and Qi will be small compared to 1. Okay, I'm in the low energy limit. So this becomes, I have a minus side. This is minus, I get plus Ig squared. Agree? J mu. G mu nu. J nu. Q0 I can neglect, so I will get minus Q squared plus M squared. Now, which piece is going to dominate in the low energy limit, in the low momentum limit? Is going to be J0, the charge. The current will be small, obviously. If I go to the limit of zero momenta, remember how the fermion, the non-relativistic at rest wave function of the fermion, the spinor looks like? It looks like this. Do you remember, properly normalized? In the limit, just because P slash is simply P0, gamma 0. So my Dirac equation becomes P0, gamma 0, minus M. And without gamma 0, it gives me immediately this form. So notice that Ji, which is psi dagger gamma I psi, which is psi dagger gamma 0 gamma I psi, which is psi dagger gamma 0 0 1 1 0 gamma I 0 sigma I minus sigma I 0. So what I get is upper is sigma mu bar 0 0 sigma mu psi gamma sigma I, sorry. I'm just looking at the current. But they are opposite. This gives me 0. It's not surprising, well, because I'm taking the momenta to be exactly the same, and actually there is a small difference. So even on Lorentz ground, you would expect the psi dagger gamma I psi is proportional to the exchange momentum when the momentum is small. So I can safely ignore it. So this is really minus I G square over Q square plus M square J0 square. With this sign. Okay? We agree? No relativistic limit. This, what is this? This is the potential in the momentum space. Let's normalize to J0 equal 1, say the charge 1. Okay? Actually, there is a density there and so on. Okay? But you and I would take something, you know, maybe the delta function to electricity. So in the usual normalization where this is U1, okay, I get that V in the momentum space is a function of Q, and it's simply minus I G squared. Sorry, the potential, there is a minus I from Feynman rules. Okay, so the potential really looks like this, G squared over Q squared plus M squared. Minus I is the rule you would associate. Okay, this is an effective interaction, so in the momentum space you put a finite I when the interaction, or if you wish equivalently, what I mean that V of R is with this sign d3q over 2 pi q e to the iq times R, a Fourier transform of Q squared plus M squared. This is the static potential. There is G squared. Notice that if I had a scalar propagator here, this is called the Yukawa theory. When I have a scalar propagator here, there will be an opposite side. So when one is attractive, the other is repulsive. Okay? There is a difference between spin 1 messengers of the force and the spin 0. Actually, even an odd. If we do the graviton, and maybe in a couple of weeks, a little later, we can discuss the graviton, or maybe you're ready at this point. It's a straightforward thing to compute this. Notice it does not depend whether I take plus or minus IQR, because I can change Q into minus Q, that changes here, the integration changes and so on. That of course will not depend. Okay, this is a well-defined thing, the sign is defined. So VR is what is it? G squared over 2 pi cube, 8 pi cube times 2 pi from the integration over 5, and then I will have here q squared dq, q squared plus m, this was ma squared from 0 to infinity, e to the I qr cosine theta d, there is an integral over d cosine theta, right? I have a front, and this is e to the qr cosine theta, and theta goes from 0 pi, so this goes from -1 to 1. This is g squared over 4 pi squared. I do this integral first, obviously, 0 to infinity. Q squared dq, q squared plus ma squared. Q squared is just now the 3 component, not the 4 component. Q squared is obvious from what I'm writing. And what will I do here? I will get 1 over I qr. And then I will get e to the I qr minus e to the minus I qr. You must have done things like this in the past. Okay, I may be boring you, but let's just be careful. Okay, so I can be a little quick. So I get to 1 over I, so I get g squared over 4 pi square r, 1 over I. Then I have integral from 0 to infinity. There is now q dq, q square minus ma plus ma square. Now notice this integral. I can change the sign here. I can let q go into minus q. So integral is going to become from 0 to minus infinity. But that's opposite than minus infinity to 0. So I summarize it if you have. This is really an integral from minus infinity to minus infinity to plus infinity e to the IQR. The other one is just a missing thing when you do it by having q going to minus q. Okay? I invite you please to check it. Which you know, where are the poles? The poles are at q is plus or minus I ma. Okay, they are along the y-axis. So obviously, I'm going to take this contour, because here, when I analytically continue, this is x plus iy, this dies off. So I pick up this pole. So what I get, this is g squared over 4 pi square r, 1 over I. Then I will have q will become, there will be 2 pi I. Okay, the sign is correct, so I have the plus sign. I will get 2 pi I, q becomes I ma. And this is q minus I ma, q plus I ma. So I'm killing the first pole, so I get 2 IMA from this contribution. So what happens to a 2 cancels? IMA cancels, I and I cancels, and we get oops, we forgot something. What did we forget? E to the minus, because of IM, and AR. I should be writing MA everywhere. Sometimes I forget to emphasize, because when the Fermi mass is coming to the game. So we found out that the potential is G squared over 4 pi r e to the minus MAR. This is with respect to a massive field. It is exponentially suppressed. Of course, it is short range. The only scale in the theory is the mass, so of course the range must be inverse of the mass. But m equals 0 is what we are after in QED, and we get the usual repulsive potential, okay? The sign tells you that it's repulsive. In the case of a scalar, it will be attractive. In the case of gravity, that I won't do today, but we can come back, you again will get that loss sign. You didn't write the thing like the propagator or a graviton, right? You're not at that level, I guess, right? This was a course in classical gravity, no? Okay, we can give it a thought if you wish. We leave it as one of the digressions. Okay. Notice it's nice that we can determine sign and everything, okay? The sign is physical. The propagator sign was physical. It has to do, remember, with the proper motion of the space, like physical components and so on and so forth. Okay, when you do the homework, you will get some more insight into the physics of massive gauge bosons, but maybe a comment just now, en passant, and then we should come back to it, that I say in the problem, let's polarize W, and it looks a bit crazy, okay, how in the world you're going to polarize W? This is not some nucleus that you have time to, you know, take and watch it at rest and apply a magnetic field, okay. But funnily enough, W does get polarized. And this is beautiful, a hadron collider, okay? So one short physical digression, polarizing W. And it has to do with the fact that the mass of quarks is very small, if you wish. It's much smaller than MW. When I say quark, I'm pretending there is just one generation, remember. For us, quarks are the constituents of matter, the things that we are made of. Okay, that's what I mean by quark, up and down quark. Okay. So it turns out, okay, this took some time to understand what is going on. In the beginning, people imagined that if proton is made out of 3 quarks, then the mass of the quark should be third of the proton mass. It actually turns out that the proton mass, which has this UUD, and the clouds of anti-quark, basically all the mass comes from maybe you know, from the dynamics of gluons inside. Okay, the strong interaction between gluons make them sort of crazily interact with each other. There is basically no mass in the quarks. If you want to know the numbers, M up and down is on the order of few MeV. So not only that it's much smaller than MW, if you wish, it's much smaller than a proton. And this is why proton and neutron have basically the same mass. Turns out down quark is supposed to be a little heavier than the up quark. But since the mass doesn't matter, they basically get the same mass. Otherwise, it would be very surprising that at that level, with that precision, they have the same mass. It fits nicely, okay? we can talk more about it, how actually I determine quark masses. If you think you're interested in this, we'll have a special lecture on that. It requires some deep thought. But at this point, I let it be. I ask you to take my word for that. Quarks are basically massless at a machine like LHC. Or basically massless, at a machine like SPS, the PP bar collider that produced W in 1983. So, what happens in that machine? That I have an up quark, which is colliding with the anti-down quark up from P, and anti-down quark from P bar. And they are going to produce W at rest. Now remember, what you've seen in the homework is that going from particle to antiparticle changes chirality. That also changes helicity. What we prove that the helicity of left is -1/2 and helicity of right from Dirac equation. Actually, it's in my notes if you haven't done that. You must have discussed this in the relativistic mechanics. Okay. If that is so, then tell me, where is the spin of up quark pointing? The guy is left-handed. Remember the weak interaction. I am, and this guy is right-handed because it's an antiparticle. So, and it all came from the interaction which only left-handed particles participated. So, where is the spin of this guy pointing? In this way. And the spin of this guy? Notice, when the W is at rest, I got it polarized. The spin of W is precisely, call this Z direction. I got SW Z +1. This is beautiful. And this is extremely important. I will show you a plot how actually W follows both the production and the decay rate follows this polarized version. Remember, which made us, if it was polarized, then remember, I write it again, d gamma over d omega should be proportional. You are going to compute it. You will see, okay, this was research only a short time ago. You will actually convince yourself that you get this theta 1 minus cosine theta distribution, which tells you that electrons like to go down if W is up, okay, let me call this up, and they don't like to go up, and so on and so forth. So this illustrative problem of parity violation, which is much easier to understand than the three-body decay of neutron, it's very hard to see physically what is going on, and to have simple analytic formula, as you know, becomes very simple in this case. So the homework actually is, if you wish, is one last convincing argument that weak interactions. We'll study the plot of the 1983 Rubia and Tal, the Roulard production of W. You will see how nicely it fits with maximum parity violation. Okay. Now, as we discussed, as I keep repeating, okay, we got stuck with this propagator, but you actually know from the solution of the homework problem that there is a way out. So what's the big deal? It's amazing that this simple thing, I don't know if you guys appreciate, that it takes years of struggle to understand what you've done in a, I don't know, half an hour calculation in a homework, okay? You see how hard it is, these little breakthroughs when you understand what is going on, okay? This is why I want you to get a picture of the development of the theory, because it looks so easy after the confusion clears. And then you are tendentially driven to complexities instead of going deeply to understand. somehow, the truth seems to be, I'm not saying that it's easy, but it tends to be simple, right? There is something to keep in mind, especially those of you who are intrigued by the complexities of string theory and so on. I can't help saying this. And the answer was, nobody paid attention, it was there in the work of Stuckelberg. Don't write mu when you write the mass term, but take another degrees of freedom, which cannot be physical, we found out. How did we decide for sure? Well, it wasn't there to start with, but we found the propagator. And it turned out that when we found the propagator, remember we had the gauge fixing term here. Let's summarize what you learned in the homework. Then the G propagator looked like I, Q squared minus psi MA squared. It depends on gauge, obviously cannot be physical. Okay. Therefore it cannot be, it should be impossible to produce it. I'm going to come to it and discuss it more carefully. I can wet your mouse and make you think. Remember what happens in QED? You do have these extra degrees of freedom, the longitudinal and timeline. But actually, when you look at the production, they cancel against each other. You never produce them, okay? Similarly, there will be a cancellation like this here, and we'll discuss it. And then the propagator for A had 4 minus, it has always to be minus, Q squared minus MA squared. See, it has a pole as it should have. And then G mu nu plus psi minus 1 Q mu Q nu Q squared minus psi MA squared. A number of comments are now important. Well, in some sense, maybe it's not surprising that people, they take it seriously. It's not the way you and I would think about that, right? Why in the world would we add the degree of freedom? We try to reduce degrees of freedom, okay? That's somehow very strange. Where is this coming from? How should I work with this guy G? Should I always take into account, for example, when I look at the interaction of fermions, my A field interacts with fermions, then obviously if you have some generic form, let me write like this. You know, W has 1 plus gamma phi, Z boson has A plus B gamma phi. In general, you don't just get gamma mu. The current is not conserved. It's more complicated. We have a broken symmetric case, A mu. Should I work with A mu or should I add? Well, it seems obvious that once I've done it here, I should be consistent and I should add and it looks like I could produce G because it's coupling directly to the fermions. Obviously, there should be some cancellation, the way it happens with the photon, right? When the time-like and longitudinal components, right? In the case of photon, you work with all 4 degrees of freedom, but they don't get produced. It has to with word identity and stuff like that, that you are probably yet to discuss word identity. You haven't done that yet. You say. Word identity says, in general, if the amplitude for production of a photon you would like this, some mu times epsilon mu, by definition, okay? It says that k mu acting on mu must give 0, okay? That's a word. When you substitute epsilon mu by k mu, okay, and that's sort of saying that the longitudinal components do not, which means, if you wish, that take the photon moving in the, take k mu to be k, 0, 0k, if you wish. It tells me that M3 is equal to M0. So when I write M square, which is mu epsilon mu square, sum over epsilon physical states, where we know we should have only m1 epsilon 1 square plus m2 epsilon 2 square. These are the different. I can safely add m3 and m0 because they cancel. This is equal to m3 times epsilon 3, which is going in this direction, square minus m0, because this is 0. Okay, they cancel against each other. Okay, this is sort of the way it goes, but I'm sure you're going to discuss this more carefully. Something like this should happen, but I should take into account. Okay, the reason I want to show you this, okay, it's interesting that if I take this seriously, and that means that the momentum space, this is epsilon mu minus plus I over m k mu g. Let's call it Q. Q mu is the exchange momentum, right? Imagine that this is P1, P2. So you would have U bar P2, A plus B gamma 5. I'm being general. U of P1. The second piece will look like 1 over MA Q mu. This is how G would couple. But now I can use the Dirac equation. This is P2 minus P1 mu. Where is my gamma mu? What's going to happen? The A piece, can you tell me what's going to happen with the A piece? The Dirac equation says that P slash U is 0, but also U bar P slash is 0. Sorry, is M? Why am I right? MU. U bar P slash is M U bar. Notice that the A piece drops out, you get, if you wish, let's continue, you will get I over MA G, then U bar of P2. This was a side comment, okay? Small digression. This I want to do carefully. This is U bar P2, so the gamma mu, the A piece will give me M minus M. It's the same fermion, okay? The U1 field does not change the structure, the property, the flavor, as we often say, okay? So I will get the difference A, then the B. The B, notice in the case of B, that P1 gives me M. But in order to act here, P2, I have to go through gamma 5. So you will get M plus M. Or there'll be minus sign. Gamma 5. U of P1. I'm using the fact that there is gamma 5 P1 slash U of P1 is gamma 5 and U of P1, and then U bar P2 gamma 5 P2 slash is minus M U bar P2 gamma 5, because P slash has to go through gamma 5, and that will change the sign. This is very important, gamma 5. Well, it tells you that, you see, this is the conserved current. I didn't even have to write that. That had to vanish. Okay, this is how it vanished, but this is just to see it explicitly from Dirac equation. Okay, the first piece, A piece, is just equivalent to saying that d mu, j mu is 0. not the gamma 5 piece. So this is 0. So what I get is IG M over MA. So maybe we could call this M fermion, just to be clear. And then I'll get U bar. I don't need to write the momenta. Okay, there is no derivative anymore, gamma 5U. It's interesting, in the 60s, people already had experience with this type of interactions, okay? They had to do with famous particles called Goldstone bosons. The Goldstone bosons, which are the product of spontaneous symmetry breaking of some global symmetries, okay? By the way, we should call them Nambu bosons. I still call them Goldstone bosons by habit. I remember in 1985 there was a conference, big conference here, and I was supposed to give a review talk on Goldstone bosons. I called it Goldstone boson. I'm going to work in the States. And I start my talk, a few minutes later, Salam enters. He often would enter late, just, he had to show who he was. Salam was emperor here. He enters with a familiar-looking Japanese gentleman. It looks familiar to me, but I have bad facial memory. I don't remember. And I keep saying Goldstone boson, and Salam is not happy. He's making faces, and then he, shouts. He used to express his opinion strongly. He says, "Can you do me a favor, very strongly? Can you call these particles Nambu Goldstone bosons?" And the Japanese gentleman blushed. Nearby there was Nambu, that I've met him before. When I was doing my PhD at City College of New York, he was a friend of Sakita, our boss. He came, actually gave a seminar, Sakita took us for dinner. So it was actually very good because the rest of my talk was very successful. And every time that there would be written on a slide, Goldstone, I would write Nambu Goldstone boson. People laughed, it makes you put in a good mood. But to this day, I often call them Goldstone boson, okay? If somehow people had paid attention to Stuckelberg, they would have realized that this strange trick of Stuckelberg, this funny, crazy touch of a genius, right? Impressive, to add a degree of freedom, to put yourself in trouble, but then, find a salvation through the brilliant, simple thought of fixing the gauge, would actually be related to spontaneous symmetry breaking. Such particles like this guy, it's not physical here, I'm not saying that G actually exists, but its interaction in this picture of our friend Stuckelberg look exactly the same as you will learn about it now in the next few lectures of Goldstone bosons. So the history of the development, of great theories, it is often plagued by ironies of fate, which somehow people that could be there to make discoveries don't read the paper, don't talk to each other. Okay, someone else comes. So the people that should have done this, like Weinberg, failed completely, whereas a 20-year-old graduate student at Hoft was basically 20-year-old when he went to a summer school, where he was taught about the problem, and a year later, extraordinary annus mirabilis, Einstein-like thing, solved everything. Okay. And this is why I want to go to spontaneous symmetry breaking. I don't want us just to take this trick. I want us to do systematically, okay? So I want to show you now, and we can actually start today, how this comes about in a simple and physically appealing picture of spontaneous symmetry break. After all, we have to break the symmetry. We have to give this W and Z guy masses. And the choice that we made when we wrote this propagator is explicit breaking. We just said they have the mass. This is how Gleshow had to do it in 1961. He didn't read Stuckelberg's work. In 1961, he could have known really of Goldstone's theorem, which was generalization of Nambu's work. The idea of spontaneous symmetry breaking starts with Nambu in 1960, and immediately generalized by Goldstone a year later, in which Goldstone proves in general the existence of Nambu-Goldstone bosons that are disk-like particles. These are Nambu-Goldstone bosons. They have very interesting characteristics. If they exist, when they exist, they couple like this. Okay. For example, if you go to the non-relativistic limit, maybe some of you that remember gamma 5 becomes off-diagonal. This becomes spin-dependent. Maybe you don't remember, don't worry, okay, we'll come to that. And another interesting characteristic that these guys have, that they are massless when they are physical particles, okay, not in the Stuckerberg's case. What was so appealing about spontaneous symmetry breaking? Well, it's kind of nice when you don't use brute force. It's just nice by itself, right? That there is a famous fable of Buridan. I don't know if you're aware of that medieval fable. By the way, this was an issue that intrigued philosophers already from the times of Persia, and it has to do with the following. Buridan says, let's imagine a donkey, equal distance from two sources of food. Donkey, says Buridan, cannot decide which way to go. Imagine that the distance is actually, it's never equal, but it can be more equal than his resolution capacity. So imagine it's really equal for the donkey. So he imagines the fable according to which donkey would die, not being able to choose. Now, that probably won't happen, okay? I don't know, we could try to do the experiment. I've never done it, but I think you would agree with me, it's more likely that hunger will make donkey decide. Once the donkey moves, the symmetry gets broken. We call it spontaneous because everything was, it's sort of the ground state made a choice. Right? The physics is specified not just by the Hamiltonian Lagrangian, but of course by the ground state. When you have a situation of complete symmetry of your underlying theory, but the ground state breaks it, we call that spontaneous symmetry break. And this is what we have to start talking about, because we will see that with spontaneous symmetry breaking, all of this will emerge naturally in a systematic manner. And we get the theory that today is called the standard model. You know some examples of, you must have read, some of you at least, which is now popular book style, some spontaneous symmetry breaking example from simple physical systems. The round table example of Salam. You know, Salam used to like the round table example. When you are at the round table, you are going to have a left-right symmetry when you sit down, because there will be glasses on the left and glasses on the right. And usually there is a convention, or when there is no convention, there is VIP, that senior or important person chooses on the left, everybody will follow. Once one person makes a decision, the rest will follow, right? If you went for dinner with Salam, you would wait for Salam. I remember the first dinner when I gave lecture, this was a long time ago, 1982. There was even David Gross, a future Nobel Prize winner. We all waited for Salam to sit down. Broke the symmetry spontaneous. Physical example that you've seen many times, you take elastic rod and keep pushing it. You have a complete symmetry along the z-axis. It will get broken, right, at some point. Example of discrete symmetry that I like, you imagine a mountain peak with two valleys. If I put a ball on the top of the mountain and there is friction, it's going to fall down. And there is no friction, so if I see the ball here, I see that the symmetry is broken. But actually just because the instability of the ground state made it. Okay. The world, if I have enough energy to put the ball here, I would actually see a symmetric world. So the simplest example would be a discrete symmetry. But let's attack the problem immediately. And let's immediately do that. This is normally not the way I teach. I decided to change it just to have more fun. You know, you can't teach the same way. I change the course a lot. But also it's good maybe to come to the crux. I took some time to motivate the direction. Let's now go and do it. This what I'm talking about is called Higgs mechanism. And this is spontaneous symmetry SSB breaking in the case of gauge symmetry. That's a Higgs mechanism. And he simply says the following: I'm going to take a symmetric theory, and I'm going to hope that I have a situation in which the ground state carries here it means that there is some charge, okay? That was first global, and I made it local, okay, like in QED. And spontaneous symmetry making means that the ground state breaks the symmetry. That means that the ground state, which we call the vacuum, I will often call the vacuum, carries that charge. It's not empty. Okay, apparently we live in such a world. Okay, it's not electric charge. We don't break that. It's this SU2 charge. Okay. So it's sort of equivalent to saying that some field, the value of that field in the vacuum will not be zero. So can that be a electromagnetic field or electron field? You see, I have a theory already at my disposal. Let me write that theory. This is the prototype of the standard model. It looks like this. I have fermions. In the standard model, I have many fermions, but they all have the same interaction given by or the same structure of the interaction. Covariant derivative. Then I have the kinetic energy for the gauge field, where d mu is d mu minus some charge in mu. So can I have a situation in which, you see, something non-trivial has to happen. And the only non-trivial thing I can imagine is that these fields, one of my fields, has a non-zero value ground state in the vacuum. Okay. Would that be possible? The answer is no, because that would break the Lorentz symmetry. You see, spinors carry spin. So if it's like saying almost the Lagrangian itself carries spin. Once you will see it actually explicitly. Okay, at this point maybe not so convincing. The same thing is true for the gauge field. Remember that I call gauge field, I call the gauge potential gauge field. In classical physics we used to call electric and magnetic field. You and I call everything field. Okay, let's use that language of field theory. Okay. To every particle we associate field. So in other words, there is something that we call, if I have a field here, then the value of that field in the ground state vacuum that I call, this is called the vacuum expectation value. Which implies that if this is non-zero, and I'd like to have non-zero, I have to break the symmetry somehow. Everything is symmetric, so that's my only hope that something like this happens. That this field must be the field that has this, the spin of that field must be zero. I don't want to break Lorentz symmetry. Of course, if tomorrow Lorentz symmetry is broken, I'm going to assume, people are already speculating this, you can imagine, there have been a lot of work on that, that some tensor-like, vector-like, spinor-like field gets a vacuum expectation value. Now, what you and I know, that the breaking of Lorentz symmetry is very tiny. If it is, because it looks perfect today. Rotation symmetry, okay. That really looks perfect. But we know that the breaking of the standard model symmetry is huge because W is actually very, very massive compared to the mass of the proton, compared to the mass of the quarks. Okay. I cannot say compared to the mass of the photon, which looks zero. Okay. So that means that I need a scalar field. I'm forced to introduce a scalar field. I can't help it. There must be a scalar charge. It must carry this charge. I want to break this charge. I'm not trying to discuss the photon. I'm trying to discuss the Broca field. I'm taking the U1 case for simplicity. It's going to be SU2, of course. In the standard model, it's the SU2 symmetry. But I don't want you to first. I always take the simple example. You know, I'm not going to prove theorems. I'm going to teach you by examples. Okay. So I'm going to take the simplest possible such field. Let's define it to carry charge 1. If it doesn't carry charge, I've done nothing, okay? Then it will not know of this symmetry. So in other words, I'm introducing to this Lagrangian, maybe I can just write here, the complex. So in other words, I'm introducing a complex scalar field. It cannot be neutral. It will not carry charge. So there will be d mu phi dagger d mu phi. Phi I don't put a factor of half because I can write phi 1 as phi 1 plus I phi 2 over square root of 2. So the factor of half will come out. Once I introduce that field, what else is needed? All this will become clear when we finish this example, which some idea we can get today. So let's take the Q of this charge to be 1. Just for simplicity. So d mu phi is d mu minus Ig a mu. Notice I write G, not T, because I don't want photon at this point. This is some other coupling G. What else is needed? I have a kinetic energy. I don't have to worry about the fermions. I just try to understand the spontaneous symmetry breaking. Let's forget about the fermions. I'm writing down the Higgs potential. Minus a sign here. Once I have the kinetic energy, I should also include the interaction, the potential. And it should be the function of the absolute value, otherwise it will break the symmetry. This covariant derivative is equivalent to saying that phi transforms as e to the I alpha phi. I alpha of x times phi. That's why this dagger here, and that's why the potential. How can I write the potential? I can expand it, right? Can it have a linear term? I will expand it in phi. No linear term, why? Because I have to break symmetry. Remember, spontaneous symmetry breaking means I start with a fully symmetric field. Okay. There cannot be a piece which explicitly breaks the symmetry. Okay. It will completely destroy it, and I'll explain to you why, the principle behind this approach. So it can start with a quadratic piece. Then I can add interactions. Can I write cubic term?
No.
Again, no. But I can write the quartic, and so on. I'm going to stop here. I take the simplest possible potential that illustrates the thing. By the way, we do stop here. The theories that we like to talk about that we call renormalizable, the theories that we can compute with a few counter terms that we will learn about, and have all the physical S-matrix elements finite, cannot have higher dimensional than 4 terms. They stop at number 4. Okay, this is what safe. Is probably gonna go deeper. Okay, so this is actually my potential. It's fair that I start with this potential. Okay. If you don't yet understand the normalizability, this is just the simplest example of. So I have to plot it. Well, it's very easy to plot it. I could plot it even in a 2-dimensional plane of phi 1 and phi 2. It looks somehow something like this. Maybe before plotting it, let's just understand. Let's plot it as a function of phi. Let's imagine, or better, let's take this potential, and then I jump immediately. M squared over 2 phi squared plus lambda over 4 phi to the 4. How would this potential look like? I will add a constant. I like to add a constant so that it touches the x-axis, otherwise it goes down. How do I know the form of the potential? When phi is very large, the potential is, I should have said it, in order the theory to make sense, lambda must be positive. If lambda is negative, there is no ground state. You will just collapse, you will fall into the abyss. So lambda must be positive. When phi is very large, I get positive large values for the potential. When, oops, I'm jumping ahead of myself. I'm very sorry. I'm too eager to do what I have to do. This is the day, sorry. M square, now how do I know what M square is? This Lagrangian would have 1/2 d mu phi square minus M square over 2 phi square minus lambda over 2 phi to the 4th. I'm just doing for simplicity 1 field, but the situation exactly the same. Then I find out here that E square is P square plus M square, right? So M square must be positive, and therefore the potential grows to phi. When phi is 0, it is 0. So it's like a parabola, only it's very steep because I added lambda. Unless lambda is very small, when lambda is 0, I get a parabola. When lambda is non-zero, if it's appreciable, it's going to be steeper. So I have a situation, okay, this is where people got stuck for a long time, in which nothing interesting happened. What is the value of the field in the vacuum? It's 0. No symmetry break. And obviously the same thing should repeat here. Just think of the absolute value of phi as this simple, naive, simple-minded case that I took. What happens if I do what Nambu did and I take, Nambu then says, why don't I try M squared negative, just to see what happens. Let me take the same potential. Let me keep this single phi real example, okay, which is not physical, but just to see what happens. So once again, the potential will be 1/2 M squared phi squared plus lambda over 4 phi to the 4th. Notice, lambda must be positive. There is no way I can even dream of making lambda, because for large values of phi, there will be no ground state, okay? They would simply fall down. Well, what happens if I do something crazy here? I mean, it seems that I'm introducing a tachyon, right? There are no tachyons. I'm introducing a field that travels faster than the speed of light, not less. But let me put it still. Sometimes things like this can happen sometimes just for fun, you know. There are things that you want to check just for, I wonder, you know, that you could have had an intuition from condensed matter physics, okay, people discuss such phenomena, okay. But it could be also one of those things that you discover. I tell you later what happened to me, for example, when somehow I managed to sort of discover something which I've never dreamed just by playing around, by being stupid, so, and not understanding what is going on. But you know, sometimes you want to do these little idiotic things. Okay, this looks completely crazy. Okay, but the number was not completely stupid. So how would this potential look like? Let's draw it. V5. For large values of phi, it goes like this. I'm going to add a constant, so I wanna go through the. I wanna touch here. Just who cares? Then what happens at phi equals 0? Notice that the second derivative is negative. D square V over d phi square at phi equals 0 is less than 0. So it's a local maximum. So it means the potential goes like this. And it's completely symmetric, right? I have an example of a computer. And it has to come here, therefore, it has to go down. That's not surprising, because dV over d phi, let's find the extrema, is minus m squared plus lambda phi squared times phi equal to 0. Agree? There are 3 extrema, so there is phi 0, let me call it, equals 0. Then there is phi plus, which is m squared over lambda square root. There is also phi minus, which is minus phi plus. I don't even have to think about that. That happens. I put them here just by adding a constant. If there is no constant, the constant is just to shift it. It will go like this. So nothing, it seems nothing dramatic at the moment. There is a certain subtle point. I'm going to try to cheat. I'm going to not mention the subtle point. Okay, let me see if you catch me. But I'm warning you, you know, I'm making a disclaimer. Now, what we want to do in life, you and I, we want to live, we want to have a stable life. We try. We don't always manage, but we try. And to be stable, you know, you should live near the ground state. You are safe if you're here. You're surely not safe here. Okay, you fall down. In other words, well, I don't know where. I have now a complete freedom. I can live here, or I can live here. Okay? Maybe Guillermo says, no, I want to live here. Okay. I claim you and I will see the same world. There will be no difference. Okay? The world is completely symmetric, so it can make no difference. Okay? We should convince ourselves of the choice. But the choice we must make. And if I take this choice, then it means that the ground state, let's call it phi Goran, is plus V. I'm going to call V squared m squared over lambda. Now, this is a ground state. Phi ground state would be. Now that means that my field phi, if I want to live here, it's not describing correctly my life. because I want to make sure that I have small oscillation of the wall. What does it mean when I quantize the field, right? I look at these oscillations, I try to live near the ground state, which we always took to be zero, but it's the first time we have to deal with that. So if I want to be on the safe side, I should write like this. H actually seems to be a better field to describe our situation than phi, because now I'm making sure that H now will be a small oscillation around the vacuum. I'm not going to go very far, because then what I say cannot be true. So all I'm claiming that living locally, and I can study the local properties of this potential, this, of course they are both function of space-time, is a better field. If that's acceptable to you, then I will proceed. Because that would imply then, we can now forget for the time being, just for the time being, that will imply that the potential is minus m squared over 2 v plus h squared plus lambda over 4 v plus h to the fourth plus this constant. I don't write the value of the constant, it's not so important. Okay? I'll have a more elegant way of dealing with that. So what I will have, there is minus m squared, there is v squared plus 2vh plus h squared plus lambda over 4 v to the fourth plus 4v cube h plus 6v squared h squared plus 4vh cubed plus h to the fourth. Let's try to organize this. There is a constant that I'm not worrying about. Notice that this is a constant. This is a constant. This is a constant. I can forget about this constant. I just want to see the interactions, the properties. I want to see the mass. I want to see the physics of H. Okay. So the linear piece. There is a linear piece. Let's. Do you see what happens with the linear piece? Well, it will vanish. It has to vanish because I'm perturbing around the maximum, of course, there will be no piece. And it vanishes because of this. So the first piece is quadratic. Where is quadratic? It's here and here. That, of course, won't vanish. What is it? I have 6 over 4 is 3. 3 half lambda minus m squared over 2 h squared. Agree? I have also lambda vh cubed and lambda over 4 h to the fourth. You know, some people, and I often do that, don't lambda but lambda over 4 factorial, because then you have to worry about the factors of lambda. I write 1 over 4 just when taking derivatives. It's a little simpler. It's only a question of name. Do we agree? Notice that this is positive. Use this, and you will see that this is equal to 1/2. I put 1/2 2 lambda v squared h squared plus lambda vh cubed plus lambda over 4 h to the fourth. This is my potential for H. There is no problem whatsoever with tachyons. H field, which describes the motion around obviously around the minimum, obviously we have a correct mass. It's all just saying that the second derivative, after all, what is a second derivative? This is, if I take the second derivative, then I take it evaluate H is 0. Why? Because I take it here. Therefore, that by definition is positive. I didn't have to do the calculation. But it's better to think later when you're doing it the first time. Okay, what I find out that mh squared, the first prediction, is 2 lambda v squared. Lambda has to be positive for the theory to be bounded from below. Because of the boundedness of the potential, the Higgs field, we call it the Higgs field. By the way, this was discovered before. In the simple case, or in the case of continuous symmetry, actually, it was there in the first person to have it was Goldstone, 3 years before Higgs. But for the case of interest, somehow the names stuck because of historic reasons. I'll come back to that because it bugs me that Goldstone didn't get a Nobel Prize. I think that's crazy, since it did have this fundamental property of the Higgs field. And his work was done in 1961. Higgs 1964. Another thing that I see, so this is very important, that the symmetry is broken when I live around here. This is this example of the ball that you put here and it falls down. Doesn't matter where it falls. There was a symmetry between left and right, which I broke explicitly, right? What was the symmetry, by the way, in this potential? I had a symmetry. I forgot to say phi goes into minus phi. In order to illustrate what is going on, I didn't write the linear or the cubic piece, okay? I wanted to have a symmetry. So this is an example of the spontaneous breaking of a discrete symmetry. They all look the same. We'll always get the same expressions, okay? It's just easy to understand because there are less components. So this is, and another important point, that there is interaction lambda VH cubed. There is no symmetry anymore. H going to minus H is manifestly broken. If I write the theory in terms of H, I will never know that there was a symmetry to start with. And I may be fooled. You already see that there will be an issue of how we are going to write, which variables to use. Weinberg has he has a dry sense of humor, actually, I love it. So he has in one of his reasonably recent reviews, he says, he's giving you some sort of like great rules of doing science well. The rule number 3, I think he called it, golden rules. Make sure you use the right variables. If you don't, you live to regret that. Actually, what Weinberg did was using the wrong variables in the case. Physics is all about the right variables. If you have the spherical symmetric situation, use the spherical coordinates. It's a much better variable than the Cartesian coordinate. You may be able to solve the problem, but sometimes the problem may look so messy that it's all a trick of choosing the right variable. Here, the original variable, what is better to use? How do you decide? This one is stupid because this is not physical. Phi is not a physical field. But it's useful because there is a symmetry. So if I want to use the properties of the symmetry, maybe I should use this Lagrangian because I have to compute things. And how do I use my Feynman rules from the Lagrangian of symmetry? So you see, in order to compute, it may be sometimes convenient to use the original stupid wrong Lagrangian, but only to understand the physics, I better use this Lagrangian because otherwise I'll think that there is a tachyon. And if you wish, what you have to learn in the next few months is to be able to go easily from one picture to another. This is what we have to do in the case of Higgs mechanism. This is often called a unitary picture or a physical picture. Unitary, you will see why the name comes, okay, I'll comment on that. And this is often called the, for obvious reasons, the unphysical, the renormalizable, you will see, okay, that this original symmetry picture will be useful for reasons of computation. And this is why Nambu wants to explain to Hsien Yang. And Hsien Yang teaches him a lesson and says, look, symmetry is either broken or not. Well, not true. Spontaneous symmetry breaking is a funny situation in which, depending how you look at it, you may conclude that it's broken or not broken. If I want to generalize it to the situation I started with, that I should. Okay, then we'll discuss the physics next time. Remember that in my case, phi was complex, and the potential was minus m squared over 2 phi squared plus lambda over 4 phi to the 4th. By the way, people, since this is not a mass, it's confusing. People often write this sort of minus mu squared. Mu is not, use m for the mass, okay? Mu is some mass parameter, but not the physical mass, which is probably better. There is even a more elegant notation. I can call it like this. If I add a constant. I pause for a second to see whether you see that this is the same thing. Notice the first piece, lambda over 4, phi to the 4th. Here it is. Minus lambda over 2, v squared, phi squared. Precisely. Previously I had v squared, lambda, I called it mu squared. Okay, this is what I got. And then I have plus lambda over 4, v to the 4th. This is my constant. Okay. This form is more useful for two reasons. One, I can read off immediately what the minimum is. I don't have to minimize anything. I don't have to look at equations of minimum, okay? Because it is definite, positive definite, okay, minimum is 0. Second, and this is sort of amusing because actually the constant does matter. We spend all these years, you know how physics is here. They teach you something and then you learn later that that was not true, and then this is true, and then that of course is not true, and so on and so forth, right? We keep growing up. One of the things we are taught, most important, that the constant added to the Lagrangian does not matter. Almost true. Who knows about this constant? One particular guy, messenger, girl, she. We have no she's this year. It's a strange situation. We never had a class before. Yeah, but before I come to the name of cosmological constant, who knows about the constant I have added here, which you call cosmological constant? You know more than maybe you should at this point. I'm just here naive. This is the, if you wish, the energy of the vacuum. You and I normally says, who cares what the energy of the vacuum is? You know, I'm interested in the potential energy above the ground. Okay, so I will define it to be 0 here, and then this has a potential energy. I don't want to, you know, test it. Gravity knows about the vacuum energy. If you look at Einstein's theory, the guy couples to everything, right? If you write the Einstein's equation, T mu nu, then here everything is here in T mu nu. Poor guy couldn't decide whether to add a term. You know, Einstein was saying, well, inside there is lambda. I cannot add lambda g mu nu. That satisfies the same equation. He would sometimes write it, sometimes take it. It's like gravitational waves. You know how he predicted gravitational waves in 1916. I don't know if you know how he unpredicted them 20 years later. He wrote a paper criticizing himself with Rosen. And it was very funny because the editor of the physical review, there was already physical review, I believe. I hope I'm right. There was no yet peer system. Okay, we have, no, maybe no, physical review probably is post-war. Anyway, the editor decided to send it to a referee who found the mistake and said this was wrong. Einstein was so angry that someone will dare to send his paper to the referee. He never published there again. But the referee was right. There are gravitational waves, as we've been witnessing in the last few years. Okay. T mu nu says you should include anything that has energy momentum, anything, vacuum or not. Okay. So this piece that we're worrying about, I don't know if you talk about it in the class. Did you? About, okay. Strictly speaking, whatever carries energy is here. But we don't worry about gravity. You and I are in fortunate situation here in this class. Well, gravity is beautiful, but but it's hard. So, and anyway, it turns out that this constant is almost zero. Gravity knows about it, and universe knows it at large, and it turns out that it's not zero, but it's almost zero. So it's safe to write something like this. At this point, anyway, it doesn't matter. Okay, I'm about to conclude. What will happen in this case? That the potential will look the way I started drawing it. This is a what you call a sombrero, a Mexican hat potential. Right? It's a well, that's how it's called. I don't know why it's associated with you guys. I'm sorry. You're supposed to be lazy, you know, sitting in the sun. You know, there were jokes when you grew up with these stupid ethnic jokes. Okay, in US, for example, typical situations. And now they get to sit side, you know. Sorry, I made this pleasure. Anyway. We also, you know, we're stupid in jokes. It's sort of funny. Anyway, so what will happen here? You're going to say that the field phi, of course, this is to be discussed in the weeks to come. We are going to take some interesting examples. In the previous case, when the guy was here, I can introduce a fancy name which is called the vacuum manifold. Actually, it has to do with the beautiful issue of topological properties of the vacuum and the so-called topological defects. I don't know if you've heard of them, domain walls, strings, monopoles, and so on. Beautiful subject. If someone is interested, I can have you read about that. But at this point, it's trivial. What is the vacuum manifold? It's a set of all points so that V is at any minimum. V at phi 0. So what was the vacuum manifold here? Well, there were just 2 points. Plus minus 3. Not very exciting topologically. Okay. This here, what is the vacuum manifold here?
Sir.
It's a circle? Precisely. So here again M0 is set of all points phi 0, so that the minimum is 0. Look at the way I wrote it. And so this is a set of all points phi 0 square equal V square, and that's a circle. It becomes interesting when you get spheres and so on. Well, a circle already has some interesting property. And of course, physics cannot depend, this is completely symmetric, which point you choose to live on. You and I can decide that. So I'm going to write phi as V plus H. I take a real value of V. By the way, notice when I said the physics cannot depend on the sign of V. For example, the physical quantity mass is manifestly a function of V squared. I will give you other examples as we go on. Okay, more interesting. This was a toy example. We would write like this. Notice a notation here. I have a field G that is going to become Stuckelberg. I'm going to get for free what I had to invent by touch of genius. Okay, I don't have to be smart now. Well, in order to compute, you had to be smart. You don't have to be smart to sort of to get there, but it's funny. I always think. I don't know if you remember when he gave a talk Weinberg last year. He said something amusing that when he does something really stupid at home, his wife tells him, you know, shut up, you couldn't even renormalize your own theory. You know? It makes me feel stupid because he feels bad. He really feels bad. He spent years. One of the reasons was he wouldn't learn path integral. And he wouldn't learn this Stuckelberg trick, okay? And when Hoff did it in 1971, I remember a year later, Weinberg wrote a beautiful paper, okay, but wrong, there were a few mistakes. He wanted to show that he can do the same. He did it one loop only. Hoff and others proved it all orders and perturbation theory that you can actually have finite S-matrix scatterings for anomalizability. And apparently at that point he says he decided to learn path integrals, okay. The thing with Weinberg, when he learns, you know. He became a master of that, it is interesting, okay. But this great master of field theory didn't want to learn path integrals. Maybe we should wrap it up. But maybe I can just tell you, we have to convince ourselves that the physics does not depend, because I could have taken any, in principle, value that is on the circle, right? Anything e to the I, whatever. I'll have to convince you of that. I wonder if you know, or whether you could guess. I'll tell you the results, so the next time we can, we had a shorter class the other day. Let me just few minutes, just to say, the thing that I learned immediately by doing the same calculation as before, that mh squared is 2 lambda v squared. It will be exactly the same. Why? Because phi squared is v plus h squared plus g squared. So notice that the physics of h is the same as before, the mass and the lambda interaction, quadratic and quartic piece. From here, I'll get this. What about g? Can you tell me what will be the mass of g? I need to do it. I have lambda over 4, v plus h squared, sorry, okay, v plus h, no, v squared plus 2vh plus h squared plus g squared minus v squared, everything squared. Agree? There's the potential, v squared cancels. So notice that because of this term, this guy gets a mass. There will be a quadratic piece which is 4 v squared h squared. This will give me the mass I said about. What about g? No quadratic piece. plus interactions. The third prediction we are making that n is easier. This looks like what is called the Nambu-Goldstone boson. You see that it has to be like that because you told me yourself that the vacuum state at zero potential energy is across the circle, so it should cost me nothing to go around the circle, okay? For example, the people offered use this variable. So maybe I could use a different name, but notice if I expand this, I will get this plus other terms. Okay, strictly speaking, there should be. This is a question of variables, okay, that Weinberg talks about. Are you going to use this variable or this variable? This variable is very useful because you see immediately the guy is massive. It's not even there in the potential. From here, phi squared is v plus h squared. Where did it go? I made it disappear. You know, like a magician. I make it become something else. You know, I really do what they do, you know. They take a handkerchief and it becomes a pigeon or whatnot. We managed to do that, okay? I can make G disappear. But it looks strange. How in the world can I make G disappear, a degree of freedom? What we'll do next time, can you guess what happens from here? Just to wet your mouth. you will actually see that from a covariant derivative, you will get G squared, V squared, A mu, A mu. And I should stop here. We are going to be systematic. Don't worry that I speeded it up. I just want you to see at the end of the day to get a picture. The cage boson is going to get a mass. I'm going to get a Proca picture. I will get it for free. I don't have to put it by hand. Just by imagining this world in which I cannot stay on the top of the hill, but I fall down, I'm going to get all the picture that corresponds to the, if you wish, standard model situation. And since I got this G, it somehow looks like I may be able to do Stuckelberg, at least notation-wise. No, physics-wise, okay. But anyway, that's what we'll do after the holidays. We are gonna study for a week or two, I don't know, 3, it depends, the physics of spontaneous integration, the Higgs mechanism. And in that process, of course, I'll have to touch upon the Goldstone picture. Any questions? Please.
Why couldn't you have just started with the Lagrangian with these fields, and you have to go through all the process of finding the potential and the symmetry breaking?
Because when I do what you suggest, this is really, this is why, you know, it took a long time for people to take it seriously. They wouldn't, because the obvious desire was just to write what Proca did, right? The problem was that I get a propagator which looks 1 minus k squared over ma squared. And this is bad. I don't know what to do with this. It turns out, this I find amazing, that the only reason they did it, I was going to say we did it, it was on B, I was going to go that they did it, is to be able to write this thing to get a nice propagator, to be able to compute. There's something amazing, that the nature conspires. It's somehow the nature is such so that you and I can compute. There are some people that, you know, get sort of a sense of vanity. And they fall in love with the anthropic principle that the third world has to be like this so that you and I can talk about it. I don't like this, okay? I remember Rocky called, once we were in a big conference in England. We were in England, this is important, okay? Rocky called the Kolben-Tanner book on cosmology that you should have, all of you possess, if you know, this is the book still, I think. Kolben said, I don't know why in the world you would ever fall for anthropic principle unless you have a perfect British accent. You know, these guys, they thought they were center of the world, right? So you can understand them. But think about that, there was always this feeling, right? You know, we keep thinking, you know, first we are special, animals are not intelligent, then you learn that animals are intelligent. Okay, but only primates. Then you learn the birds are intelligent. They make tools. Then you keep learning, you know, that we are not in the central position in the universe and so on and so forth. But still people like anthropic principle. One of these reasons is, you can understand them sometimes. The desire to compute. And the only way we know how to compute is perturbation theory. We are ignorant. At the end leads to a profound Higgs physics in which actually there is a Higgs boson. There's even Weinberg, who's sort of, with his great sense of humor, he even wrote a very important paper for lovers of anthropic principle. That if you believe in anthropic principle, and that means that there ought to be galaxies today, okay, at least we had to be able to create a universe. He found out that cosmological constant had a limiting value, this. That became a celebrated paper that in this field of anthropism. But recently he wrote something very nice. The guy who speaks a lot about the anthropic principle is Linde. one of the sort of fathers of inflation. And the other proponent is Martin Rees, a well-known British astronomer. Well, he's got a perfect British accent. We should understand him. So he says that he's willing to bet the life of his beloved dog on anthropic principle. That's nothing, says Linda. I'm betting my own life that this is true. Says Weinberg, that's nothing. I'm willing to bet both the life of Martin Rees' dog and Andre Linde's life that this is a good principle. I would subscribe to that. But that's an answer, okay? The only reason I'm bugging you all of this, and this is why I wanted the introduction, and this is where some of you felt, well, maybe let's just do it. I want you to appreciate this incredible thing, that all of this fancy development was just for me to be able to compute. And amazingly enough, it turns out to be a deep theory of nature. Actually, it became, the standard model started to be a theory of weak interactions. That's all I had to do. That's all I wanted to do, remember? And I had a theory, it was Fermi theory, okay? But I couldn't compute. So I said, no, I got to do better, right? So I took psi w, or z. I still can't compute. So then I go and say, okay, I'll introduce a trick like Stuckelberg, which is spontaneous symmetry breaking, okay. Turned out I'll be able to compute. Lo and behold, Higgs was found. And it seems, it's not yet proven, but every day we get more and more evidence that the particles do get mass from the Higgs mechanism. This is somehow very, very deep and profound. Elementary particles. Not you and me. Remember? Please keep in mind, you and me, you and I not, because you and I are made out of protons, not of electrons. Electrons have no mass whatsoever. And protons get a mass from these crazy dynamics, okay? So this is strange, okay? As deep it is in elementary particle world, as irrelevant it is for us. But here we are studying elementary particles, okay? So for instance, this is... And I'm glad that you asked me this question, okay? Because I'm an inertial learner. I don't want to learn what I think this was basically a laziness the way I was a street kid. I used to like to play. So I don't like to learn unless I'm forced to. Well, one of the reasons, if you make me learn things that I don't have to learn, I don't have my feet on the ground. It's an advice that I will give you. Be careful when you learn new things. And that's the reason I want to teach this fact. I also would not want to learn this. I would just want to work. I would have, well, this was nicer. There was some dynamics. This today seems completely far-fetched, right? Instead of going linearly, I went somewhere else to later come back. Okay. Sorry, taking this again. I still find it exciting the way this took place. It happened such a long time ago. I was there when it was happening. I still find it exciting. Find it unbelievable. I feel exciting. Weinberg, he says, you write these equations, and it's hard to believe that the things you write actually describe nature. It's easy to believe what Newton wrote describes nature. Not when you do it. It looks like a game.
Press the button.